Welcome to Rubber Duck Engineering. This week, we're going to continue our exploration into machine learning. We're going to do reinforcement learning of tic-tac-toe, which means we're trying to teach a neural network how to play tic-tac-toe. Uh, Normally, this is where I would throw over to Eric, but Eric isn't here this week, so we just have me. So last time we did machine learning, we were using TensorFlow to do things with bridge. Now, it turns out bridge is kind of complicated. So I thought it would be easier if we simplified the game that we were studying. And so tic-tac-toe seemed like a good choice because it's a pretty simple game that I think we can understand, which means when our machine learning is going wrong or we're messing up, as we usually do, we'll have some better chance of understanding what it's supposed to be doing. The other change that we've made is we've sort of teched up, and instead of using TensorFlow locally, we're now using Pytorch on the Azure cloud. And I learned this by taking an online course in machine learning. And what I discovered is the machine learning people have really embraced this notebook technology. So if you've ever used Mathematica, might be familiar to you, at least that's where I'm familiar with it from. But the idea is you have this sort of interactive web page here that is somehow a cross between an editor and like a REPL. So in here, you can write some code. So let's say I want to do my Python import statements. I can type Shift-Enter, and that will cause those statements to execute. And for example, I can run these statements, and they'll all run. And now I can run this statement. And now if I want to insert something here, I can make a new cell in my notebook, and now I can just type more Python code. So let's say I want to examine this state. I can just run it, and it will print out the output right here. And this is like super handy. I can totally see why the machine learning people love this paradigm for interacting with computers, because it's really aids in exploration, because you can try things, you can tinker with things, you can sort of see what your variables are like. If you messed up, you can go back and edit things and try them again. It's like really highly interactive, and I'm kind of amazed that this notebook technology hasn't taken over more of the world. I can totally see other places, like in the same way we have like hot reload in Flutter to experiment with user interfaces. I can totally see like a fusion of like Dartpad and Flutter and these notebook technologies could be really neat in the UI space. But anyway, so here we are trying to do some machine learning. So I started out by just creating a little scaffolding for a game of tic-tac-toe. So an important concept is we want to represent the board state in tic-tac-toe. And there are a bunch of choices for how to do this. I decided to try to go with something related to the one hot methodology in machine learning. So the concept for a one hot representation is you have a big matrix full of numbers, and then you use 0 to mean something isn't there, and 1 to mean something is there. And so for tic-tac-toe, in the 3x3 grid of tic-tac-toe, each cell could either be empty, which obviously should be represented by 0, or it could have an X, or it can have an O. And so I figured a good way of representing this would actually be to have two 3x3 grids. And then if there's an X, I'll put a 1 in one of them. And if there's an O, I'll put a 1 in the other one. And then wherever there isn't an X or an O, I'll put a 0. And so that's what this create board function does, is it just creates two 3x3 matrices, one to represent us, the player whose turn it is, and one to represent them, the player whose turn it isn't. And then I just stack them up. So now I have a 2x3x3 cube of numbers that are all zeros. And then it's also convenient to deal with very flat indexing spaces in machine learning. Like you often end up with like a single vector that represents, let's say, all the possible moves that we can make. And so I wrote this little function to unpack just the move index that say, break it out into an X and a Y. So then this is valid move function just says, if it's out of range, that's not a valid move. Otherwise, break it out into X and a Y, and then go check that in our state at X and Y, this colon means in both of the plies, so both for us and for them, we're expecting a 0 there. They all have to be 0. in which case that's a valid move because no one's moved there yet. Then this is the make move function. It basically asserts that you're making a valid move, breaks it out into coordinates, breaks out us and them, makes a copy of us so we don't mutate the state. We always create a new vector, and then just assigns one in for us, and then stacks them. And here I flip the order, so I put them first instead of us first. And this represents sort of passing the turn to the opponent. It's now the opponent's turn to move. So after the move function, it's us is now them because it's the other person's turn, if that makes sense. And then this is just a quick function to check whether somebody has won in a given 3x3 grid. It basically looks for 3 horizontally or 3 vertically, or it looks for the diagonals. And then to check like a score, break out us and them. If we've won, then the score is +1. Seems logical. And if them has won, so if the opponent has won, it's -1. Otherwise, the score is 0. Nobody's won yet. And then another thing that's very important is to know whether the game is over. And so the game is over if you add up all of the ones for both us and them. So you sum up the X's and the O's. If you get 9, then all the squares are filled. We're done. Or if the game score is something other than 0. So if one of us or them has won. And so now we can explore this sort of very simple tic-tac-toe model in this notebook. So we already created a board. We already printed out a state. You see we have our 2 3x3 grids. This is us on top and them on the bottom. And then we can check, like, is move index 6 a valid move? So that's going to be 0, 1, 2, 3, 4, 5, 6. So is it valid for us to move there? I think the answer is yes. We can try to make that move. So here you can see I just very freely edit this. Then I can say, what's my state? So now I pointed at this square before, but of course, because we flipped us and them after making the move, the 1 actually shows up there because it's now the other person's turn. And so they have not made any X's or O's, and we've made our X and O here. You can also just freely edit these things by just doing them. That's the 2 Ds for those of you playing along at home. So we make this move, we print out the state, and what's the score? Score is still 0. Nobody's won yet. So let's make some more moves. Take a look at the state. So now us has moved once here. They has moved here and here. Get the score. Score is still 0. Make another move. Score is still 0. What is the state? The state is something like this. I see I changed it, so it's not actually going to be complete. So is complete is going to be false. But I bet if we move right here, then we can cause us to win. So let's make a new move here. Let's make a move. This is going to be position 0, 1, 2. Let's move for index 2. Look at our state. Of course, it's flipped over. So what was previously us now is them, has made a horizontal connection. So is complete is true. And let's look at the score. Score is -1, meaning they is 1. Hi, thanks for joining us. Or I guess me. Used to saying us because I used to having Eric here. Cool. So we have a basic model of tic-tac-toe in Python in this sort of notebook form using these tensor data structures. And so now the next step is we want to actually add some neural networks and do some machine learning to do this. So I think we're going to try a technique from reinforcement learning called deep Q learning. So I've discovered this area is like highly academic. So every time you find a tutorial about how to do machine learning, it sort of ultimately is a representation of some academic paper, which means everything has a crazy name that is some academic made up when they wrote their paper. So deep Q learning is based on this Q equation, which I'll write here as a comment. The idea is it's all centered around this function Q. And so what Q does is it takes a state and an action, and it's going to predict for you what is the reward that you get for taking that action in that state. And importantly, it's not the immediate reward. So you don't necessarily win the game by putting a X in the middle of the tic-tac-toe board. It's after you've taken a series of moves, and after your opponent has taken a series of moves, what is the sort of uh, reward that you could expect to get in total time? And so, in order for that to work, there's this discount factor called gamma. So you can't just like add up the rewards from an infinite sequence of moves. You want to basically shrink the value you get from every reward by this factor gamma so that the sum converges. And so then you're left with this sort of recursive equation, which says the value that you get from this state is the like immediate reward plus the best reward, so argmax over like a prime, right, of q of state prime, so the next state, and taking that action. Then you have to multiply by this gamma factor. Makes sense? So like it's the reward you got by taking this action right away, and then the discounted uh, reward you would get from the next, the best action that you could take in the next state. And what's neat is from these two functions, you basically train Q as a neural network, and you don't really have any clue what Q is, but you use this sort of recursive um, function to iteratively approximate Q and cause the whole thing to converge. And then once you have this, you can decide like what move should I make? Well, the move I should make is max is just max over a. You want to say argmax q of state and a. So the move I make in a given state is this. So it's find me the a maximizes this value. Return a, don't return the value of q. Somewhat sensible? I thought it was a neat trick. So we're going to try to see if we can actually make this work. So I'm going off of this tutorial here, which I will present briefly. I'm not sure why I can't present it, but it's I'm not sure why I can't present the tab. Anyway, it's a tutorial from toptal.com called Schooling Flappy Bird, Reinforcement Learning, a reinforcement learning tutorial. So on this website, he teaches the neural network how to play Flappy Bird. And so it starts with an image of the Flappy Bird screen if you played Flappy Bird, and it figures out like when it should, like when the bird should flap its wings so it doesn't crash into the pipes. So we're going to do a sort of similar thing, but we're going to do it for Tic-Tac-Toe. Hey, thanks for joining us. So the first thing we need to do is we need to create a model. So I'm just going to steal his model, which is totally wrong for our application, but we'll make it right. So his model involves, these are just a bunch of parameters. We'll save those off up here for now. This thing involves a bunch of like, 2D convolution layers, which are not really what we need for our thing. So for our thing, we're just going to need a bunch of linear layers. So we'll just cut these down. This. Oops, we lost our layer. So fully connected one. Sure, I never know what numbers to put in here. These numbers always seem very mysterious. But I don't know, let's try a 64 to 32. And then I don't know what this in place means. Maybe I should look that up, but I guess I'll try it. And let's do another one from 32 to 32. We can adjust these numbers if for some reason these are not working us out. Right. And then we need to basically, the last layer, we need to project down to the number of actions, which in our case is 9. There are 9 possible actions. Bar today. Yep, it is just me today to try to entertain all of you with this machine learning stuff. Eric will be back next week. He just had a obligation this week. Okay, so now we need to write the forward direction for our model. So mostly we just want to be invoking these functions that we've created. To then return out. The view is going to be important. We're going to need that in a second. So we present the input into this function in this highly structured form, right? We present it in as a 2 by 3 by 3 tensor. And what we actually want to do is we just want to reshape it into just 18, just a vector of 18 things. And so I think I looked this up earlier. I don't think we actually want to use view. I think we want to use, well, let's try view. I'm just going to look up what Pytorch view does. They have all these fancy functions for basically reshaping your tensor without actually reallocating the backing store of data, because it's like it's expensive to actually move the memory around, but not expensive to change your view. So it takes a D type, same data as type, but of a different D type. Okay. So I think that means this is going to do what we want. We want to do, actually, I think this is exactly what we want. So that the out size, we want to preserve the batch. So the first index is actually, so we thought we had a vector of 2 by 3 by 3. Actually, we're going to have a vector of batch size by 2 by 3 by 3. So we want to preserve the batch size, and we want to destroy everything else. And so I think this will do something. We can test it and see. Anyway, and then we'll feed this through all of our layers, and we'll see what we do. Let's try to see if that will compile. Oh no, very sad. What did I do wrong? Maybe I need like a class here. So the nice thing about this notebook style is, like normally in a Python REPL, if you mess up, you got to go like retype all your things. Yeah, I did a solo episode maybe about a year ago. You can look it up. It's the one about building a render tree in JavaScript. It was fun. It's obviously more fun for me when Eric's here, because I can trade off some of the talking and try to talk for an hour straight is not something I have a lot of practice in. But I mean, there are definitely people who do like these kind of shows all as one thing. So I suspect if I practice for a while, I could talk for an hour straight. Okay, so now we created our neural network. And so I think we could just try feeding, let's make an instance of it. What happens if we just apply a model forward to our state? Let's do this in 2 steps. Let's first create the model so we have it, and then we'll say model.forward of our state. We need to make it. Let's make a batch. Let's make a couple of them. So let's make our mini batch. That's just going to be torch stack. Board, empty board, the current state that we had from that game. Let's look at our mini batch. Mini batch now has two instances of our game. So actually, let's try this view thing and see what this does. So hey, Static, thanks for joining us. So let's try this view transformation because I'm really slightly unclear about how that's going to work. Let's put well, first of all, let's just try the beginning part of it. So the size, I'm expecting this to be the dimensions of my tensor. So I'm expecting this to be 2, 2, 3, 3. 2, 2, 3, 3. Episode 101 is missing. We did broadcast it live, but we have taken it down from the archives. It featured a product that a friend of ours had worked on, and he wasn't super jazzed about how how we basically failed to use his product very well, which is normal for us. Like we failed to do everything on the show, but he didn't like how his product was presented, so we took it down out of respect. Okay, so then the zeroth dimension of this size, this is just going to be 2, which is basically the number of items in my mini batch. And now we're going to figure out what this view thing does. So view -1. So this did exactly what I wanted. So now I still have my mini batch structure. So I have 2 items in my batch, and then I'm expecting there to be 18 of these. Put that into a variable and do x.size. 18, cool. Yeah, okay, so that the view thing is doing what we expect. So let's try to actually evaluate the whole model on our mini batch and see what that does. It blew up. Great. Why did it blow up? Okay. These shapes cannot be multiplied. Oh, okay. That seems legit. So I had 2 by 18 and 64 by 32. Okay. So, okay. Maybe I need to say my input here is 18 because I have 18 entries. And then I want to have an output size of 32. Then I'm going to do my 32 to 32. And then I'm going to do my 32 to my number of actions that I can take. Seems logical. Okay, so let's recreate this. I don't need to recreate my mini batch. When I'm running, I'm doing Shift Enter to run it. So let's see what this does. Aha. So this actually computed something. So in principle, what these should be is the expected reward for taking action index 0, taking action index 1, etc. Of course, it's totally random, right? Because we haven't taught the model anything. We just initialized it with random garbage, right? But at least it produced numbers and didn't explode. So that seems like a good start. Okay, excellent. So now the next concept that we need from this tutorial is we need to have a memory. So one of the tricky things about reinforcement learning is it's pretty apparently unstable. So it's highly influenced by things that you see. Like it's very path dependent. You can think about it, right? Because you pick an action and then you sort of go down that path and then you see the rewards down that path. And if you're not careful, your model will get fixated on that. And so the approach, apparently this comes from a DeepMind paper where they were trying to play Atari games, is what the paper was about. This is an old paper. I think this technique has evolved and gotten better over time. I'm just sort of starting at the ground floor to try to get my feet wet and learn how this stuff goes. So apparently the technique that they had in this paper, which seemed to work at least for Atari games, and it works for Flappy Bird, and maybe it might even work for Tic-Tac-Toe, is you keep a record of the actions that you've taken and the states and rewards that you saw with them. And then you sort of explore the space by sort of trying out random moves or slightly biasing towards moves you think might be good, fill up your memory, and then you periodically train by grabbing random sets from your memory and then training on those. And so you sort of keep coverage over all the different paths. So an important step to do that is to create this memory class. So let's do that now. Named a tuple is not defined. Cool. Let's go find out how we get named tuple in Python. All required to import something. What do I have to import to get name tuple? Python works. You probably do without name tuple, but name tuples seem cool. From collections, import name tuple. Cool, we can do that. So I'm going to go back up here. So this is the neat thing about the notebook, right? I can go back to my imports. I can just add that. I guess C comes before T, and just rerun that cell. And now I've imported it, and I've sort of kept the structure of my program intact in some ways. Okay, so let's see if this worked. Good times. So what is this doing? So this is just an object that has a memory, which is a DQ, and we're going to push things into the memory, and then we have a way of sampling from the memory, and then we can pull out of the memory. And I think the way a DQ works is if you exceed the capacity, it'll just forget the earliest thing, and so we'll keep in this way we'll cycle through and keep sort of more recent things that we've seen. Yeah, it was based on React, the previous episode. I've used React once or twice. Also, not super familiar with it. Hopefully, this episode is easy to follow. I guess it does require some amount of Python to understand, but I find Python very easy to understand. Like this is the constructor, right? So this gets called, and self is like this that just shows up. These funny things are like ways of getting like multiple arguments and then like exploding them or something. I never really understood. There's also like a double star, which is for like keyword arguments or something. Never really understood, but this seems to work. Okay, so we have the replay memory. That's good. So now the next thing that we need is we have our neural network. Right. We need to make an optimizer, and we need to instantiate our memory. So we can totally do that. So here we have our model. Optim. Problem. Pretty sure Optim comes from Torch. Python is easier to follow. Okay. Set. DQ is not defined. I bet DQ is in collections too, if I had to guess. Yep. And then I'm not sure where random is. Maybe I can just import random. Oh, seemed happy. I never know in Python. Like, do I have to reevaluate this? Might as well try. Okay. This is happy. Okay, so let's explain what this is. So this is the root mean squared optimizer. So root mean squared is you take the observation you have, you subtract it from the thing you wanted it to be, you square that, and you add that up across all of your dimensions, and you take the square root of that. Also called the L2 norm. It's a very normal kind of error measure. And so this is an optimizer that's going to try to optimize the root mean squared error. Fair enough. And then I instantiated my memory to have a capacity of 10,000 observations, which I have no idea if that's a reasonable number or not, but it's the number that was used in the tutorial, so we'll try it. Okay, so now we're going to attempt to do the select action step. Add some state. Okay, so this part here is, remember we talked about we need to balance our exploration and our exploitation. So to maximize exploration of the space, we would just make random moves all the time. But that will probably lead us to visiting parts of the state space, like taking sort of nonsensical actions in Tic-Tac-Toe. And so as we learn more about Tic-Tac-Toe, we want to start biasing our actions more towards actions we think will lead to winning the game. And so as we train the model, we slowly adjust between taking a random action and taking an action predicted by the model. So let's attempt to make this code do something like that. So we need start and end. I'm just gonna grab the numbers that they had. I think where did they start and end with? Okay, I'm just gonna take all of their constants. Let's put this here. And I want something below this. Oops. They're constants. Okay. So start minus end. So start is like 0.9, which means 90% of the time we'll take a random action. And then at the end, we'll 5% of the time take a random action. So take this and multiply it by an exponential. So we'll exponentially approach 5%. We'll remember that we took another step. And then if our random guess was above threshold, we will, okay, so now we got to figure out how to apply this to our actual situation. So our thing is called model. Take model the state. We'll take the max. So that we'll try to take the thing that we think has the biggest reward. We'll select it, and then we'll turn it into a one-by-one view. Okay. And then otherwise, if we're supposed to be picking a random thing, we'll take a random thing where a number of actions is called number of actions. We don't need this device type. A little bit unsure about this, but we'll find out. Okay. So let's create a new state. Clipboard. See if select action in that state does anything reasonable. Blows up. Excellent. Now we probably need to import math. Awesome. I feel like if I was working in a fancier IDE, it would figure out all my imports for me and just import them. Maybe that's a thing that Java IDEs do that other IDEs don't. 4. Okay. I mean, 4 is a fine thing. And when I was about to put in my mini batch here, I would kind of expect to get an action for each item in my mini batch. Okay, so maybe I messed that up because I'm only getting one thing. I kind of wanted to get more than one. Let's just, for the sake of simplicity here, let's assume we always do the random one. Okay, so we're always going to pick random. I should validate that my mini batch has the proper, like it's a batch of 2. Okay, let's try to select. So I'm always getting. So this doesn't seem quite right. When I see why it's doing this, it's getting a random from that range. Is there a way to get a REPL in a notebook? I mean, it kind of is like the whole notebook kind of is a REPL. Like it's it feels like a REPL. Like it basically lets you do multi-line REPL. Like if I just like keep typing in this thing, I do like 2 + 2, and then I do x equals 3. Print out x. I say x equals x + 2 + 1. 2 print out x. Like it is a REPL, right? But in the style where you don't keep editing the same cell, you keep going down, you keep track of your history. And then when I've been working with these notebooks, I find what I do is I sort of create this big mess. And then when I go back through it and I clean it up and sort of keep the parts that I wanted to keep and just delete the parts I didn't want to delete. And then there's a function you can do in here, which I'll try, which is basically, it says restart kernel and run all cells. And so that's a good way to check that you haven't like left some state in the Python environment. So this thing, okay, I'm going to lose everything. It's fine. So it's now going to go back to the top and just execute all of these statements that I did in order and repopulate the output directories. So you see here, something happened. Oh, this was no good. I messed this up. So I'll fix that there. Luckily, that one is a comment, so it's not going to mess anything else up. Oh, but it stopped, you see. So I think if I press play here, this will say run the selected cells in advance. I think there's a way of going and do it all. Run selected cell and everything below. Yeah. So it'll go through and redo all this stuff, and I'll still be in this sort of sensible state. So this strikes me as not quite right. This one here. Let's look at the other case. Let's assume that we always decided to move according to the model and not according to random. And happens here. Oh, it blows up. Okay, that's good. Let's find out why. Shape 1.1 is invalid for input of size 2. Yeah, the notebooks are super cool. Like if you've never played with a notebook before, I would recommend trying it. You don't have to like spin up a whole Azure instance. Like notebooks are like super well integrated into the world. It turns out, like when you commit to GitHub and you have a notebook, GitHub has like a native interface for showing you the notebook, and like Visual Studio Code has like if you edit a notebook in there, it like has a notebook editor built into it. So the data scientists have like been everywhere, and they've taught all of our tools about notebooks, and we never knew. And I don't know, they're pretty cool. Okay, so this is not legit. We messed something up here. So let's just try playing with this piece of it in isolation and try to figure out what we did wrong. So we have our model and our state. Let's just start here. What is model state max 1? Oh, even that is no good. It's mad. Oh, we need mini batch, sorry. Mini batch max 1, okay. This is something that involves a tensor with 2 things that looks kind of legit, right? It said, I think it found the max. Can I compile Python in Dart compiler? I think the Dart compiler doesn't know how to compile Python, but I bet there's a way of teaching this notebook tool how to interact with Dart, and then we could have a Dart style notebook. I haven't tried it, but the thing's called a Jupyter notebook, and it allows you to select your interpreter. And I'm really curious what happens if you were to select just like the Dart command line interpreter as the interpreter. I haven't tried it, but it might be neat to try. Okay, so the next thing I'm supposed to do is get the 1th thing out of this. That's my tensor 2, Seems legit. Seems like I selected move 2 twice. And then now why do I need a view on this? What is the point of doing view 1.1? Maybe the comment will tell me. Max 1 will return the largest column value for each row. The second column max is index where the element was found. So we pick the action with the largest expected reward. That makes sense. So why do I need this extra .view 1.1 thing? That makes it mad. View 1. Let's try getting rid of that and seeing how comparable that is. This thing is now gives me a tensor of 2, which is a seemingly sensible thing to do. Okay, so now I'm going to put back this randomization. Check. Here. And I'll leave the comment on that. Okay. Great. Batch. I think this might be okay. There's a thing, they have this concept called broadcasting in all these machine learning things. And so the idea is if you try to operate on this with more entries than it has, it'll just make copies of them. And so maybe what they're doing is they're saying, no matter how big your mini batch is, this will get broadcasted or replicated that many times. And so it's not that important to actually materialize all of those entries. I guess they're all correlated. You only draw random ones. I used a Jupyter Notebook once, but I basically treated it like a normal editor and didn't enjoy it. Yeah, I think that the thing of it that makes it nice is you could edit all in one giant cell, right? And if you edit everything in one giant cell, it's basically just like a normal editor. Like if you scroll to the top, right, you see that, oh, I have all this code all in one giant cell. But that's not actually how I typed it in, right? I typed it in one function at a time. I said, okay, let's make the create board function. And then I played with the create board function, make sure it worked the way I wanted it to work. It's very sort of like it's the opposite, sort of the opposite of test-driven development. Like the test-driven development way to do this is you would be playing with it by writing all the tests for it. Here I was playing with it just by being interactive with it. And then I wrote the is valid move function, right? And then I played with that for a while. And then when it was all done, I cleaned it up. I deleted all that intermediate experimentation, and I collapsed all of the definitions into one block here. And then I just treat it as one block, and I'm not too worried about it. I think the reason why it works well for data science is in data science, you do a ton of exploration. You're trying different things, you're tinkering. Like, we're going to come back and tinker with all these numbers here and try to make them work. And it's less about like, we're building up a big software system. Like, the unit testing becomes very important because everything is supposed to do exactly what it's supposed to do. In data science, like if you get something that's like 95% correct, that's like really good, right? And so what does it mean to unit test the thing that you're only really expected to be 95% correct? And so it sort of ends up being, you sort of want a different style of programming. And I feel like that kind of pattern applies well to user interface, especially if you're in the design side, right? Where what you're trying to do is you're trying to play around with different experiences, maybe different interactive modes, and you just want to like try different animation curves, try different springs, try different like visual effects. And so feel like this kind of playful environment, which you get some of with hot reload, but you could also get a little bit like the notebook thing might be fun too. Anyway, I've been really enjoying the notebooks. It's sort of by the way, the course that I took, it's if you want to find it, it's called course.fast.ai. That's a website. It doesn't need a .com or anything. And the guy who teaches that course, it's taught by a couple people, but there's a main guy who does most of the lectures, and he is like the most notebook fan of notebook fans. Like, he wrote the book for his course in a Jupyter notebook, which makes total sense, right? Because he's got all these code examples and he wants to make sure his code examples are correct. So he can just run his book. Like, there's a way of, let's try to figure out how to do this. We've only been using code cells in here, but there's a way of, let's see if I can figure out how to do it, of getting a markdown cell. And then you just start typing markdown. How do I make a markdown cell? Oh, markdown. Okay, so let's make a new cell. Okay, and let's change it into markdown. And now I can be like, try to use select action, right? And when I complete this, it looks like markdown. I can go in here and edit this just like any old markdown. And so he wrote his whole book like this by using select action. See if it works. Batch. Right? It's just like, so like you can have this thing that's a mix of documentation and code, which we do a lot of, like even in Fuchsia, we have a bunch of docs, and then we have this problem of the code inside the docs rots. And so we have these scripts that extract the code segments, execute them as tests to make sure that all the code in the docs are correct. But this is sort of a more natural way of doing that, because your documentation that you wrote in Markdown and the code thing that you're writing, they all like inhabit the same space and work together. I think it's super cool. I've really been enjoying it. Okay, so we got the action selector. Great. It's sort of this funny stateful action selector that's going to change over time. But YOLO, global variables are cool. We're here for it. Okay, so now the next thing we need to do is the training loop. Okay, so this is like the crazy function that we're gonna try to figure out together. Here's the training loop. Okay, so we don't need this anymore, right? So now you can see we tried all this stuff. Exciting. We can just go delete these. We're convinced about our select action function. Okay, here's our training loop. Let's try to figure out what's going on here. Okay, if the length of our memory is smaller than our batch size, forget it. We're not going to try to optimize our model. We haven't seen enough yet. We wouldn't know how to do it. So now the next thing we do is we sample from our memory the batch size. What is batch size here, just for concreteness? Is 128. this many transitions that we've seen. The transitions are going to be state, action, next state, and reward. Now we do this crazy thing, which we're going to have to figure out what it does. Transpose the batch. So this converts a batch array of transitions to a transition of batch arrays. Yeah. So like we're somehow like we had like a vector of transitions, and what we wanted was a transition where each of the items in the transition was a vector, because then we're going to stack them up and execute them in parallel. All the machine learning stuff is really highly rotated on these vector computations in these batches. I don't have it set up on this cloud machine, but you can get cloud instances that have GPUs, and then you can run these computations on the GPU, and they're like a bazillion times faster. But I haven't quite teched up to that level yet. I'm just sort of still on basic CPU execution. Okay, non-final mask. Oh, right. So that's an important thing. So this equation that we talked about way back here wasn't quite right. So this recursive equation, this holds sort of in the state. Oh, maybe I should make this a markdown. So while we're doing this, that would be a logical thing to do. Markdown the Q equation. So say like is an extender towards yeah, I'm gonna try to pitch it to the docs team. Let's see what they say. I kind of think they're not going to go for it because they have a big fancy tool they like already. This equation only makes sense if state prime is non-final. What that means is if it's possible to take another action in the next state, then this equation makes sense. Otherwise, state prime is final, which means no more actions are possible. Okay. In that case, we don't need to do this recursive thing. We've reached the base case of the recursion. And so all that we need to do for this Q equation is we can just skip this part. The reward is what it is. My markdown isn't beautiful, but it could be more beautiful. So now we need to account for this in our training. I don't know if Rust and C++ notebooks are a thing. So part of what makes this work is it's sort of the REPL-y nature of it, right? If you're running, I mean, you could write a Rust notebook, but you would be oftentimes like you often have to write like a big impl block, right? That contains lots and lots of code, and so it's hard to break that up into cells. Whereas in Python, because Python is sort of designed with the idea that it could be used in a REPL, it sort of applies nicely to here because each cell is like a little mini REPL. And so I would look at languages. I mean, Dart was designed to be used in a REPL, right? Or any language of that type. I think would probably fit nicely into this format. Okay. So what we do is we go look at S being none. So if the next state is none, that means that that's final. We don't need device. A fancy device. Okay. And then next state. This says S for it basically filters out the S's that are not none. I expect there's a more Pythonic way of writing that. Okay. Concatenate state batch. That's the state that we started with. The action that we took. And the reward that we got. Okay. Okay, compute st model predicts, right? So let's put our model. We put in our batch of states, and then we gather one in the action batch. Okay, so what does that do? Select the columns of the state. These are the actions which we would have taken for each state according to model. Okay, makes sense. So now we need to compute the reward for state s plus 1. Okay, so the next states are take a bunch of zeros. Okay, next state, non-final mask. Okay, so the ones that are non-final, it's here we're just going to use a single model for both of these. It's fine. The non-final states, next one detached, right? So here's where we're using our model to predict the so here, remember our Q equation, we use our model here to estimate this quantity, which in the beginning is going to be garbage, but should eventually converge to something. Okay, compute the expected Q values. So we take our next state values, we multiply it by gamma as we saw, and we added the immediate reward to that. And that's our guess for what Q should be at this state. And then we say we want to use this funny loss function, which I don't know. So this funny loss function is basically, it's like a V with a little, instead of coming to a point at the bottom, it comes to like a rounded off point. Some of these, like, why do they select various functions in various places? I have no clue why they do this, but we could use L1 loss here, and then we would just have a thing, but fine. They want to use this one with the smooth. Okay, state action values, expected action values, unsqueeze. Okay. Okay, so now we actually do the optimization. So here's where all the cool stuff happens in Pytorch, at least as I understand things. So we say, okay, we're going to start computing a gradient. So we computed this function loss, this value loss. And then here we, Pytorch in the background, all the computations we're doing, they kept track of. And they said, oh, you added this, you multiplied this, you took in these parameters, and you did these things in a way. And then what this is doing is it's running that computation backwards and computing the gradient. So it's saying, it's figuring out for every input parameter in my model, how does perturbing that parameter by a little bit make this value go up or down? And I think that's so cool that it can like remember all that stuff. Okay. And then what we do is we look at our model, we clamp them, and then we tell the optimizer to take one step, basically nudging our parameters. I'm not sure why we need this. We'll come back and see if we need this. Nudging our parameters to make the loss function go down. Okay. I'm a little concerned that we haven't taught it anything about tic-tac-toe yet, but hopefully that's coming soon. Okay, so that's optimized model. So now this is the last function that we need, and maybe it'll even work in 7 minutes. We'll find out. Okay, so we're going to run 50 games of tic-tac-toe. Maybe we'll do more than that, but we'll start with that. So this is the ith game of tic-tac-toe. Reset the environment. I have no idea what this is. Uh-oh. The environment is the game. So this is like our board equals create board. Okay. Screen size. We've got our board. Okay. For t in count, what is count in their world? Count is not defined, but why don't we say while not is complete board. Okay. We haven't completed, maybe we'll call this state just for the sake of consistency. We create this state while we're not complete. Select an action. Great. So now we need to get our reward. So in our world, the reward, now we're teaching about tic-tac-toe. So what do we call our get reward function? We called it get score. Okay. So step we called take action, right? So let's say our state is make move state action. Okay. And then our reward is done here, which is going to be separate. Our reward is get score state. And then I'm going to negate this because remember, after we made a move, it's now our opponent's turn. And so, like, let's say we won, then the get score will give -1 because it'll now be the opponent's turn. So I'm going to put a minus there. And then done is going to be is complete. Is complete in the state. Okay. Now reward is just a tensor with the reward. Okay, very good. Observe the new state. We don't have to do any of that. Okay, if next state is, so let's call this next state. Score is complete, blah, blah, blah. So if it's not none, let's set the next state to none. All right, so if we're done, set the next state to none. That seems sensible. Okay. Push this thing into our memory. So we need to remember the state that we were in when we started, the action we took, the next state that we arrived at, and the reward that we got. Great. Advance to the next state. Optimize the model. If done, so this is just while one. We'll just do this forever. While true. Okay. Try to optimize the model. If we're done, then append to the episode durations. We don't care about that. We don't care about plotting. We're just going to break out. And update the target network. We don't need that. We didn't have a separate target network. Okay, so we can just say, while not done. Or while state is done. Okay. All right. Go. This is like the moment of truth. Okay, it's super mad. Okay. So somewhere deep inside of our code, we had a 2x9 and a 18x32. Okay. So let's try to figure out what we did wrong here. So we fed. So we're in select action where we had the trouble. We try to apply the model to the state. So I think we have like a vectorization problem here, where we have sometimes we have a batch of one, and sometimes we have a batch of a lot of things. And I think we're not quite prepared for that yet. We can select action. We're always going to have just a single state, not a mini batch of state. But our model is set up to take a mini batch. So I think we should just torch this unsqueeze. I think this might be unsqueeze. Because yeah, I want to make a tensor that has one more dimension that's a 1. So I think that's either squeeze or unsqueeze, I would think. Maybe it's unsqueeze. I'm looking it up in the docs over here. Yeah, loops of the kryptonite notebooks. I mean, I could break it down into a function, right? Unsqueeze. No, that's not quite right. Maybe cat. Cat. Yeah, I can see what you're saying. Cat. Okay, I'm going to do this a simple way that I know how to do it, which is to say torch tensor. Well, let's just test that in a little square down here, right? So let's take a foo equals createboard. Foo. All right, and I want to make this into a mini batch. I think I want to say like torch tensor. Only equivalent tensors can be converted into Python scalars. Ugh. What program do you open mini-dump files in? So mini dumps are this is different than a mini batch. So mini dumps are like crash dumps that have had a lot of information redacted in them. I don't know how exactly to analyze them. We just have a program that analyzes them. It basically loads them up, and I think you can maybe just be able to open them directly in the debugger. You try opening them in ZXDB and see if you can open them. Let's stack. What is bar going to give me now? So I added one more. One here. Okay, so I'm going to use stack. I guarantee you that stack is not the most idiomatic way of doing this, but I think it's going to help us here. Okay. Invalid syntax. We messed this up somehow. Stack. We need one more parenthesis. Okay. So let's try this again. Still mad, but it's mad for a different reason. So we've made progress. Make move action. So what is action? We can delete these. Now we get into this, a little bit of my frustration with Python is that I don't know what the types are. So select action. I think select action is returning us a tensor. Let's go see. Let's try select action. State. What I really want is just the actual value. So type item. I guess it's probabilistic. That's fine. Okay, so let's go back here and do item. Okay. Oh, it's right. So it picked a random move, which totally was not valid. That's legit. So maybe we need to set the reward of an invalid move to like -1. If not is valid move, state action, and state is none. The reward is -1. None is true. True. Else make the move. Okay. Okay, we got a lot farther. We're now in optimized model. Oh yeah, I think Visual Studio opens mini dumps. No, I think it is. I think this thing all originates from Microsoft. Okay, we're a little bit past an hour, and we're sort of in the debugging the thing stage. So I'm inclined to go for a little bit longer. Batch action. So why is it mad? Expected tensor is element 0, but got int. Okay, that sounds plausible. Okay, I think we're going to go for 5 more minutes and see if we can get it. So can we print out batch here? See batches. Okay. Batch is a whole lot of stuff, which makes sense because it's supposed to be a batch. So let's try to print out batch.action. Batch.action. Oh, it's a bunch of things, but sometimes a tensor. Okay, so we have some sort of type error here where it's often just a number, but sometimes a tensor. Interesting. So I wonder what we're pushing in here as our action. Like sometimes, depending on what's going on, like whether we're picking the random move or not, we're going to sometimes put in a tensor and sometimes not. 5 expected a tensor got int. Interesting. Well, it seems like it's always supposed to be a tensor. Oh, action. Oh, select action item. So I bet I'm not supposed to put item here. So I'm supposed to say is valid move. So raw action is action.item. Okay. Move. If my things were smarter, I bet they would work on tensors. Okay. That's still mad. Okay. Still sometimes get a tensor and sometimes not. So maybe something is wrong here. Maybe my model is supposed to return a tensor. Tensor. Like, what if I force it to go path? They're going to give me a tensor. Add. What did it do? It gave me a tensor. It just gave me a different shape tensor. So maybe I'm supposed to stack it once. I feel like I'm a little bit like hitting it with a hacksaw, but part of that is because I'm feeling. Oh, maybe this is this view 1.1 thing that we took. It's coming back to bite us. Slightly stressing out because we're getting to the end of the hour here. Okay, that looks like the same shape that random gave us. So why don't we try this back together? These are supposed to be comments. Indented one more. Okay. Let's take the print out of here. We're gonna try this. Okay. I feel like we got close. We didn't quite get all the way today. Maybe next week we'll come back and we'll actually be playing Tic-Tac-Toe and see if the neural network can beat me at Tic-Tac-Toe. Anyway, thanks everyone who came live, and I'll see you next week. Bye.